Okay, so let me say a couple of words about the next homework. The first problem is let G be a finite group. Show any element of G has finite order. So essentially, what you're proving is that little trick I did yesterday with the Rubik's cube. How if you start with a solved cube and do anything to it, do it over and over again, it'll come back to the original solved position. Number two, show any group of exponent 2 is abelian. What does it mean to be exponent 2? Let me remind you what that means is every element in the group has order either 1 or 2. Any such group is automatically abelian. It's interesting to note that this problem is false if you substitute for 2 any number bigger than 2. There are groups of exponent 3, 4, etc., etc. Not abelian. Number 3 is kind of a magical mystery tour. The goal of this problem is to show that any finite group generated by 2 elements of order 2 is dihedral. And I'll tell you what the dihedral group is actually today. Suppose that G is generated by the elements x and y, both of which have order 2. We'll also assume that x and y are not inverses of each other. Number A, assuming that the order of G is finite, what can we say about the order of the element x, y in G? This is deceptively easy. Number B, show that the group generated by x and y is the same as the group generated by x, y, and y. And finally, show that the group generated by x and y is dihedral. Okay, so we'll some of these words here we'll explore today. For the next problem, let me recall for you what a field is. You probably heard this word passed around in linear algebra. A field is a generalization of real numbers, rational numbers, complex numbers. Basically, what it is it's an abelian group, and if you throw out the 0, it's also an abelian group under multiplication, and you have the multiplication and addition play nicely together. Distributed problem. So this is a generalization of, like I said, things like the real numbers, the rational numbers, complex numbers, Z mod 2, Z mod 5. Number 4, suppose F is a finite field with Q elements. These things exist, but whether or not they exist doesn't matter the problem, we solve it anyway. Let T and F be the collection of n by n upper triangular matrices over F that are invertibles and a non-zero determinant. Prove that T and F is a group and count the number of elements in T and F. You may use anything from linear algebra that you happen to remember, just quote me the theorem or tell me the result. You don't have to form the theorem. Finally, 5, you don't have to do. These are G problems, but I put them out there for you anyway. These are extra credit problems, just for fun. You can turn them in for extra credit. Number A, show that if n is odd, then precisely half the elements of the dihedral group on n beyond order 2. We'll see what that is for. You know this notation. This is the symmetric group on 15 elements instead of 3 that we did last time. So it's the number of bijections from the set of 15 numbers to itself. So it's got 15 factorial elements, big group. Find an element of the largest possible order in SVT. So that's just kind of for extra credit. Any questions? All right. Okay, so I'm probably going to spend the bulk of the day talking about a number of examples for your toolkit. So here's we've seen some examples of groups before. We looked at the integers, we looked at Z mod n, we looked at some matrix groups, we looked at S3. Here are some examples, and I'm going to start. I'm going to start with this word you heard before, the dihedral. So geometrically, we do this group this way. This is symmetries. A regular. And you're all assumed at the end. Regular. So let me tell you what I mean by this. I'll start with a couple of simple examples. That is supposed to be an equilateral triangle. Forgive me. Imagine that you're putting together a puzzle and there's a missing triangular piece that you have to put back in there. So you get your triangular piece of the puzzle. How many ways are there? If I had a triangular piece of the puzzle, put in that hole, how many ways can I put that in there? 3. I certainly see 3, right? Because if I have my piece of the puzzle, I can, whatever the top, the top angle is, I can put it here, here, or here. Everybody agree? I certainly see 3 ways to put that in. Great. Are there any others? You can flip it over. I can flip it as well, right? So when I start with this top vertex, I can either put it in this way or I can flip it over. So it looks like there's actually maybe 6 ways. Let me be more careful and go over sort of more illustrated. Let's do the pentagon here. And let me label vertices. How many symmetries? How many ways are there for me to see? Well, the vertex called 1, I can either rotate here, or here, or here, or here, or I can leave it alone, right? Everybody agree with that? 1, 2, 3, 4, 5 different ways to put that pentagon in if I only just rotate it, right? But I can also flip it. So in other words, here's one way I can rearrange it. This is just a pure rotation. And turn, let's like what? Clockwise 72 degrees, whatever it is, right? And another thing that I could do like this. What's the relationship between this and this? I flipped it around the y-axis. So it looks to me like this. Just from spinning it, I've got 5 ways to arrange this, right? And then if every one of those has a partner that's obtained by flipping it around the y-axis, right? So it looks like how many different arrangements are there here? Looks like there's 10. So in general, if we have a regular pentagon, then there should be how many symmetries you guess? How many ways to
And symmetries?
2? There should be 2 in symmetries. And pure rotations. Right, in rotations of 2 power n, one's twice all the way around. And each has a flip. Y-axis. This group is called dihedral group. You'll see in some books they'll have the notation 2n because that's the number of elements. I use this notation here, dn, is that just means that it's symmetry. In fact, I'll list them the elements. Yes. R squared S. R. These are all the arrangements where R, rotation by 2 pi over n radians. And S is flipped throughout my axis. Right. So one, this just means I didn't do anything to it. This means I rotated it 2 pi over n, 4 pi over n, 6 pi over n, blah, blah, blah. And this is actually this is the inverse of R, because when what happens when I rotate the n-gon n times? I'm back to where I started. Everybody agree with that? And so infinity. And what is this? This means flip it. This means rotate it and flip it. Rotate it twice and flip it, and so forth and so on. And this is like function composition. So this is all the standard rotations, and this is rotations with flip. Right. Now let me ask you something. Here geometrically, and I'm gonna come by this after the symmetric groups away, but yes.
And are we specifying which, whether it's a clockwise or counterclockwise rotation?
I did not, and you can do either one you want. I'll do it
The other one,
clockwise.
seconds.
So let me ask you this. Suppose we have R. So I'm gonna draw this way. 1, 2, 3. This is my very big gun. Okay. So this is supposed to be my apex here. What happens when I do R to this? This becomes, if I rotate this 2 pi over n clockwise, this becomes now the top n. 1, 2, n minus 1, 2. Everybody agree? And what happens if then I do S? What does this look like?
So then if they pass,
Okay. N, and this is n minus 1, n minus 2. This is 1. I agree with me? Is that, yes,
So when going back to the D sub n, are those states or you said function ones? What were the R's, the S's in that set? Are they states or are they
you can think of them
functions?
as states.
States,
Yeah.
okay.
Right. Let me ask you this. Is doing RS the same thing as doing S over? So what if I flipped it here and then rotate? Well, in fact, let me go through, and this is a fundamental thing about that I want to actually start here. 2, 3, n my n, and right here. Let's first do S. which flips it. So this will be one n minus one, et cetera, and be two. Now let's say we do r to that. So I flip it, I rotate it. So that if I rotate it, it's going to put the 2 at the top. One. Right. One and etc. And this would be 3, 4. And what happens if I do S again? Well, I'll flip it again. We'll have 2 at the top again. 1 n. That's going to be 3, 4. Does everybody follow where we are here? So I started with this with 1 at the top. I flipped it, I rotated it clockwise, and then I flipped it back. Can somebody describe a shortcut to getting this move? This is the counterclockwise rotation. This is the fundamental definition of how the diagonal works. Flip, rotate, flip, it's the same thing as going backwards. Right. So for example, sometimes you see the dihedral convert this way. It's generated by R and S. That means everything in there is a word made out of R, S, and their inverses, perhaps. With R to the N is 1. That means when I rotate this thing in times, I get it. And flipping twice is the identity, right? If I flip back when I started. And SRS are inverse. So you can use these rules to show that there's only n things here. So for example, in D5, one R squared, R cubed, R4, S, RS, R squared S, R cubed S, R4S. Here we have R to the 5 is 1, S squared, and SRS is R inverse. By the way, what's another way to write R inverse in this particular dihedral group?
Yeah.
Part of the,
Part of the 4.
which is the same thing as R4 here, because R5 is 1, so the inverse of R4 is. Right, so R inverse is R4, right? So if I gave you what's that element? I promise you it's going to be one of these to me. Let's simplify this a little bit. And these are the rules that I'm playing with. Ooh, look at that. What's SRS? And I'm going to say R inverse here. So first step of many. Right? So this is now R5. And what's R5? It's the identity, right? R5 is the identity. So that's gone. What is S squared? S squared is also one. So I can shortcut this to R squared S R cubed S R S R. Everybody agree with that? I look at this, I'm kind of cherry picking here. What's SRS? It's R inverse, right? Which conveniently kills this. So this is now R squared S R cubed. Right. How do I go further?
Big supports. I would say.
Okay, yeah, you can do that. Let me also kind of rewrite this a little bit. I can multiply on the left, and notice this is RS equals SR inverse. If I multiply on the left by S squared is one, leaving me with RS here. Everybody agree with it? And that puts that S here on this. So this is good too, because this right here is R squared S R and SR is by this identity here. Oh. Yes, I guess I want on this side. Well, that's fine. R S R. I'm going to use this. This is SR inverse. And that R inverse cancels this one. So I get R S R R. Everybody okay with that? And I'm going to do this again because RS is this. So this is, I'm going to replace this with this, and that's going to be SR. Now, the way I listed the dihedral group, that's when I listed, I'll use the identity one more time. This is, well, what is SR, by the way? All right, this is. That is cool. Again, you can use this fundamental identity to say that SR is R inverse S. And if you want to write this in terms of positive powers, I made this up on the fly, but any word that you make out of R's and S's, respecting these rules, you can get it down to the form of power of R between 0 and 4, and either an S or nothing in there. Any questions on this? We're going to see the dihedral group quite a bit, and I'm going to get this from another point of view in just a moment. I'm going to generalize also symmetric groups, and I'm going to show you how to do some computations there. There's a big theorem in group theory that we haven't gotten to yet. But basically it says, if I walk up to you on the street and give you a group, it is a subgroup of a symmetric group on the set. So in a certain sense, any group that you could ever find, the one on the Rubik's Cube, the integers, whatever, sits inside of some symmetric group somewhere, as long as it's big. Right. But A set, we'll play the next one. So we have then S of A is the set of F from A to A. So it's F, right. This is the set of all functions from the set A to itself that are both one-to-one and onto. Okay, here's a couple of questions, right? What happens when you take a bijection from A to A and compose it with another bijection from A to A? What do you get? Another bijection, right? Y'all remember that part from 3190, when you have a bijection and a bijection, and you compose them, you get a bijection, right? Everybody okay with that? This is closed under the operation of function composition. Okay, is function composition associative? Yep, got that covered in 3190. So got that going for us. What do you suppose is the function that goes from A to A? And when you compose it with any other function that goes from A to A, it leaves it alone. The identity function that takes everything in A to itself. When you compose that with any other function, nothing changes. Everybody okay with that? Does a function from A to A have an inverse? Well, I asked that question, not necessarily, but what do we know about these functions here? They are bijective. They're one-to-one and onto from A to itself. So all you got to do is run the arrows in reverse and you get your inverse function. Everybody agree with that? So this is actually a group. A group of functions group under function composition. So last time we worked at, yes, sir.
What did you mean when you said the way I asked that, not necessarily?
Because the way I asked it, I just said it's a function from A to A, does it have an inverse?
Oh,
And not a general function won't.
Yeah.
But if it's bijective, you're good to go. Okay, other questions?
How would the group, is it like F cross F equals? Or would it be like F1 cross F1 equals like F3?
No, so the way it would work is, so if you have F1 from A to A and F2 from A to A. So notice the domain and range both the same. The domain and codomain are the same. It's one-to-one and onto. Then the new function, when you compose them, this is the new function from A to A. And if this is a bijection and this is a bijection, then the composition is bijection. Okay. We went through the painstaking details of this, or some painstaking details. We worked this out with the set A, one, and I call this group S3. Y'all remember how many bijections there were? There was 6 of them, and it was annoying to write down because I had to write up 6. If A is a finite set within elements, then SA is written S. So we had a set of 3 elements last time, so we looked at S3. These are incredibly important groups. And in fact, the first time I myself ever solved the Rubik's Cube, I did it with a pencil and piece of paper. I'm not very good at looking at things and figuring them out, so I had to write something down. And I used symmetric groups, and on paper I said, okay, this is going to work. I used that to do this. So these are very powerful things that can conquer a lot of stuff. But how do you use them? So SN, the group of bijections from the set of n things to itself will have how many elements? N by 4. This group gets out of hand very quickly, right? Let me give you a practical example. how many corner pieces does this have? Like pieces on this cube that have 3 colors on them. 8. Everybody agree with that? S8. When you want to understand how the Rubik's Cube moves things around, you've got to consider an S8 because it permutes. Basically, it moves the corners around, right? I mean, if you ever spin this cube around and this thing ends up in this position here, you've got big problems, right? They always end up in these 8 positions here. And what you're doing is it's a bijection from the 8 corners to the cell. S8 has 40,320 elements in it, right? And nobody wants to write that, right? So how do we deal with it? Yes.
I was saying, is that why when you were doing the cardinality of the Rubik's Cube, you had a bunch of factorials?
That's exactly right, because it's got these symmetric in it. And actually, it's worse for the pieces with 2 colors here, because there's 12 of those. And S12 it's out of hand. So how do you compute? So we're going to be doing this for practical applications stuff. I want you to know how to do this. Let me give you a couple of functions here. Okay. I'm going to call this first function F, and 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, and 5 goes to itself, we'll say. And this function G, 1 goes to 3, 3 goes to 5, 4 goes to 2, 2 goes to 1, 5 goes to. Now, of course, I could. So what happens when I do? Well, okay, I can just follow the train. Do F then G. 1 goes to 2 back to 1. 2 goes to 4 to 2. 3 goes to 1 goes to 3. Heavens, Betsy. 4 goes to 3 goes to 5. 5 goes to 5. 4. So when I compose these 2 functions in that direction, it actually leaves 1, 2, and 3 alone, and it swaps out 4 and 5, right? Nobody wants to break this crap, right? And what if I was looking at S12, right? Let me show you kind of a way to abbreviate this using this example. I am going to express this in what's called cyclic notation, or cycle notation. Okay, where does F take 1? Here, just F, not F composed with G. Where does it take 1? 2. 2. Okay, now where does F take 2? To 4. Where does F take 4? 3. And gosh, the last one, 3 better go to 5. I'm sorry, it goes to 1. And that closes that off. What's left off out? 5. Where does 5 go? That's all it's out. So this notation means 1 goes to 2, 2 goes to 4, 4 goes to 3, 3 goes back to 1, and 5 goes to the cell. In some notations, you might just sometimes people suppress the ones that hit themselves just to save time. Let's see if we can do G. How does G work? Where does 1 go? 3. Okay, and how about 3? Where does it go? Okay, how about 5? 4. How about 4? Okay, I've used up all 5. Where does 2 go? 1. And better. Cycles back. So let's see what happens. What happens when we do uh, I'm gonna write it this way, because most books use this notation. Oh, it's 1 to 4. And I will suppress the 5. I'm not gonna- I write it this way because we're gonna do this from right to left, backwards looking, because it's function composition, right? This function acts first and then, everybody okay with it? It doesn't matter where you start, but I like to be a bookkeeper. Where does 1 go? Well, let's see. First one goes to 2. And then 2 kicks it back to 1. So 1 goes to itself. Everybody agree? How about 2? 2 is the first number I haven't done yet, so let's see where it comes to. 2 goes to 4. To 2. Right? How about 3? 3 goes to 1. The 3. 4 is the first number I haven't seen. What happens to it? 4 goes to 3. 3 goes to 5 and stuff. So 4 goes to 5. Now there's something very wrong if I'm going to go back to 4. Let's see what happens. 5 goes nowhere, still at 5. There's no 5 here. And then to 4. And that's exactly what we got. Swaps this out.
Well, five does go somewhere, 5 gets back to 5. Because there is a difference between
Oh,
5
yeah,
not
that-
going anywhere. and-
Well, going nowhere, I mean to itself, but it was nowhere different. Okay, let's do one. It's got more teeth. I don't know about you guys, but I've always wanted to know what this function is. Today is my lucky day. For example, this first one is the function. What does this function do? It takes 1 to 2, it takes 2 to 7, it takes 7 to 6, 6 to 5, 5 to 3, 3 to 1. And anything that's not in there, like 4, goes to itself. Right? What happens when I compose all these functions? Well, I always start at 1, be a good bookkeeper and pay attention. Where does 1 go? It goes to 2. And then to 4. No 4, no 4. To 2. Back to 4. No 4, no 4. It's done at 4. Let's see that. Where does 4 go? No 4. Aha, goes to 6. To 7. To 5. Let's see that. Okay, now you guys take a look at that. See if you can tell me where 5 goes. Does everybody agree with that? 3 goes, I'm sorry, 5 goes to 3. To 1. To 3. How about 3? Where does that go? 3 goes to 9. How about 9? 8 goes to 8. How about 8? Well, right, 8 goes to 9. To 2. To 1. So it goes back to a number we've seen, so that closes off the cycle. Do I agree with it? Have I accounted for all the numbers? No, I haven't. What's the smallest number I haven't accounted for? Okay, start a new cycle with 2.
Thanks.
Two. Where does two go? It goes to seven, have to do it with that. Right, two goes to seven, to one, to four, to seven. How about seven? Where does it go? Two, that's right. That does funny things. It goes to six, to two, to three, to one, to two. Okay, if we counted for all the numbers of the period, what's missing? The smallest one's missing seems to be six. Six is the only one that's missing, right? What has to happen to six then? If this is a bijection. It has to go to six, but this is me we're talking about, so we better check. Let's see what happens to six. It goes to five, to six, and it's done. How about that? Okay. So when you compose these functions, this is what you get. And this is the function. In fact, I can draw this function for you. Actually, I'll do it over here where I've got some board space. 1, 2, 3, 4, 5, 6, 7, 8, 9. So after we compose that big mess, what does this function do? It takes 1 to 4. It takes 4 to 5. It takes 5 to 3. It takes 3 to 9. It takes 9 to 8. And it takes 8 to 1. And then it swaps out 2 and 7 and just goes to 7. That's what that function looks like after all this work. And this is much better, isn't it, than writing 1 through 9 with arrows for this function, this function, this function, all of it, right? Everybody feel like you can do this now? Okay, so practice this because it's a useful way to think about things. So matrix groups. We're actually going to spend a good chunk of time on the symmetric groups later. Here's another good example. We talked a little bit about these last time. Let F the so this means that F under addition is an abelian group. I found this actually in the homework. It means when you take F and you jerk 0 out, so you remove the 0, then the operation under multiplication is an abelian group. And for all A, B, C in the field, A times B plus C is AB plus AC. This is called the distributive problem. So you've actually kind of got two groups going on in the field. You have everything under addition is an abelian group. If you remove 0, then under multiplication, you've got an abelian group. And what you're calling addition and multiplication, they play together nicely. That is, A times B plus C is AB plus AC. Familiar examples of this are things like rational numbers, real numbers, complex numbers. If you look at Z mod P, where P is prime, this is also a field as well for any kind. And the linear algebra that you all took in 3110, how many of you took a linear algebra course where the focus was over the real numbers? Right? I mean, I almost always use simple reals. You might have done some stuff with eigenvalues and stuff. We started messing around with complex numbers a little bit. But actually, everything you did in linear algebra basically applies over any field that you want. Notation I'm gonna let M and F be the N by N matrices with entries. Number two, if you see this notation here, GLNF, this is N by N matrices. With entries in F as above, with determinant not zero. These are the invertible matrices, the ones that have an inverse. And three, SL in F is N by N matrices with determinant one. Some of you were asking about the notation. This means general linear. This means special linear. This forms a group under addition. This one is a group under multiplication, because what happens when you multiply two n by n matrices that have non-zero determinant? You get an n by n matrix with a non-zero determinant, right? And this one is actually a subset of this, because I don't know much, but I do know that one is not zero, right? So everything that lives here lives inside of here, right? But this one is also closed under multiplication, because what happens when you multiply a matrix of determinant one times a matrix of determinant one? What do you get? A new matrix of determinant one. Here is a theorem. And this is actually a little bit more sophisticated than the homework problem that I gave you coming up. Let F be a finite field. With two elements. You've heard me say it, so you can believe me, and you can probably show it yourself. If you look at Z mod P, then that is always a field, and it has exactly P elements. So this is always possible for any prime to the first power. Is there a field of P squared elements, P cubed elements? And the answer to all of that is yes. For any prime P and any natural number N, there is a field of that order, and it's unique. It's not a fact. But we need a little bit more to. Right now, we only know that there's ones of P, but these all exist. Then how many n by n invertible matrices are there over a field of Q elements? Well, yeah, we'll argue that. That is true, finitely many, because there's only finitely many set matrices. Yeah. Where Q to the n minus Q minus. So, for example, Actually, let's do this. If you have a field of 49 elements, right? So the number of elements would be 49 minus 1, 49 minus 7, and then the next pile is too big. So the number of elements, if you have 2 by 2 matrices of a field of 49 elements, the number of ones that are invertible, 48 times 42. So I'm going to give you that formula just for fun. I want you to think about why this might be true. I'll give you a hint. It's linear algebra. Think about how to put together a matrix that's invertible. And we'll talk more about this on Monday. Let me remind you that I have to be out of the office from noon until that exam is over. But when I come back, I'll be available to you till my 3 o'clock meeting. So if you got any last minute questions about the homework, come give me a holler. Okay, any questions? Yes, sir.
Either 5 or.
Okay, so I learned this after many years of teaching experience. It is due at 1, but you're not really. This is what you need to set your goals for. That's when my office hours usually end on Friday. You're going to be okay if you get it in before the window closes at 5. And I need to close the window because if somebody's late, they need to come tell me about it instead of, turning it in 2 weeks late and then I don't see it's there kind of thing. So, all right. Any other questions? Yes, ma'am.
Still have office hours till 12?
I do.
Okay.
What is the, like, L2? Why is that two? I don't know.
That's just an example out there.
Oh.
So what I mean here is 2 by 2 matrices over field with 49.
If the field is over 49 elements, it's like a fire away though. And it's not, that'd be. That's 49.
Yeah, like I bet other cats too, like I get that.
So you got 4 things to
No,
go
it's
in, right?
It's frank.
And for anything that you more or less got 49 choices. You got the field. So what I'm doing is I'm following this formula here. In this case, your field is 49, that's 7 squares.
No.
So you just.
Wait, how do we? Right. Like, it's the.
It's 49.
No, or in one is. Okay.
You're my field is 49.
It's
So that's, yeah. So there's. Yes. This should be. So I'll correct, so this should be, my N here is 2. And my Q is 49. So this should be, shouldn't it, 49 squared minus 10. And this should be 49 squared minus 49. And then after that, so it's much bigger.
Yeah.
Right, so that's what it should.
I'll do this.
Uh,
That's right.
okay.